Okay, as we said last time, this last chapter for the semester is now going backwards. We're instead of doing derivatives, which is what we spent the first 13 weeks doing, we're now going to spend the last 2 weeks doing integrals, which goes backwards. The first thing we're going to talk about with integrals is called the definite. We have two types. We have definite and indefinite integrals. One of them is within a certain bound. The other one goes to infinity. So let's look at this. The definite integral, the definition. We always begin, let f be a continuous differentiable function on the closed interval AB. J is the definite integral of the function over that interval. So J is simply the value that represents the definite integral. J is equal to the limit of the function as I equals 1 to n of our function times our. Because remember, what are we looking for with the integrals? What are we looking for with integrals? We're looking for areas under a curve. So whenever you have to find the area under the curve, or actually it's the rate of change also, but we're looking for the area under the curve. J is that value what we're looking for. It's the limit as n approaches either infinity or 0. What we're going to look at for this time is we're going to look at as n goes to 0. What does delta x represent? The change of x. So delta x is b minus a, or x I plus 1 minus x sub I. It's the width of each interval. Because how are we finding the areas under the curve? If we have a curve that's on this closed interval, then what we're going to do is we're going to take small rectangles. Each one of these are delta x in width. And it's not always going to be the same size, because we can have a function that is very steep at points and very wide at others. So because of that, it changes its width. So the delta x is the width. And what does f of x represent? Well, here's a function. There's the function f of x. But if that's the width, this is the height. So in other words, base times height is equal to what? Area. So we found the area of this rectangle, then this rectangle, and this rectangle, and this rectangle, and all so on and so forth. That's why we add them all up. That's why we add them all up. This is what's called the Riemann sum. the limit as the partition goes to 0 of the summation of all your values. That's called the Riemann sum. Now, I got to relate this to what we just talked about. The letter P stands for what's called a partition. Partition is simply the x sub k's. Each one of these x's is a partition. It's the how wide they're apart. The partition with those double bars on both sides is called the norm of the partition. When we use the word norm, in this case, we're looking for, it's short for normal. Since all the partitions are not of the same size, we have to figure out a standard equation to use for all these. So the norm is simply largest P in the set, or of the set of all P's. Because we're going to try to err on the side of caution. It's better to have too many than not enough. If we looked at the norm as the smallest one, then we'd underbid and it could be disastrous. And it's hard to get the average of all the delta x's or the midpoints because they're all different sizes. So we just simply look for the largest one. So that's what that stands for. So what this says is if the norm goes to 0, what does that mean? Delta x sub k. Well, it's actually x sub the x sub k plus 1 minus x sub k. It's the size of the width of each of those intervals. That's what a partition is. So the norm is the largest of those, of all the sets, because this P and this P and this P, all these can be different sizes. So we take the largest one. As the largest one goes to 0, what does that mean? That's the same as saying as delta x goes to 0. As the width of each rectangle goes to 0, what happens to the rectangle? It becomes smaller and smaller until it becomes what? So at first, delta x could be this big. Then it could be half of that. And then eventually, it becomes a sliver. It just becomes one line. Because there's no distance between the two sides. It's just one line. So as the delta x's, as the width goes to 0, we add them all up. Now, what does C sub k represent? C sub k is the midpoint of the delta x. As we saw in chapter 2, if we look at the area from the lower bound as opposed to the upper bound, the higher bound, the values will become different. If we look at from the lower bound, we get this entire rectangle. If we look from this one, we get that rectangle. So we're missing some pieces. So what we do is we find a C sub k that's midpoint in all these intervals. So if this was x sub k and this was x sub k plus 1, C sub k is right between there. It's the average. How do you find the average? If you had 2 test grades, how would you figure out the average of your scores? Add them and divide by 2. So that's what you would do here. So C sub k is actually x k plus x k plus 1 divided by 2. It's the average of those. The reason for that is because now we're taking the height of each rectangle as being the middle point. So that'll mitigate some of the overcharging and undercharging. So that is what we call Riemann sum. That's the value of, if we add up all these slivers when p goes to 0, so it's a bunch of single lines, we add up the each unit one times how tall they are and add those up, we get the area of that curve. So far, so good. Now, how does this relate to what we're talking about in this chapter? Integrals. In the old days, it was Sir Isaac Newton and Gottfried von Leibniz were trying to invent calculus. Fortunately for us, we use Leibniz's symbols, not Newton's. Newton's symbols were confusing at best. So we use Leibniz's. When we look at the integral, that symbol there means integral. And we have numbers at both ends. This is, okay, these are both integrals. If you have an A and B, this is what's called a definite integral because it starts at A, ends at B. If there's nothing there, this is called an indefinite integral. Reason it's indefinite is because there's no beginning, no ending. So the area under that curve, it's always indefinite integrals will always have whatever thinks the answer plus some constant. You always have to have that plus c at the end of indefinite integrals because we don't know what extra stuff there is. So for both of these, we have to have the operation. The x, it doesn't have to be x, it could be anything. It could be f of t, dt, it could be f of u, du, it could be anything. We call these letters here dummy variables or dummy arguments because you can put whatever letter you want to in there. It doesn't have to be x. We just use x because f of x from algebra, f of x is the same thing as y. So x and y. Do you want me to walk through the entire definition of where that came through? Because it all starts with the Riemann sum, which is a summation of k equals 1 to n of our function. And then how we extend it, make it j as our limit of that. I'm not gonna go into too much of that because I'll probably bore you almost, but I know you guys want to go, well, how do we use it? The formal definition is important, but all you really need to know is what the formula really tells us. Okay, so remember the limit goes from, since it goes to n, it goes to infinity because we don't know how many we have. And n is our simple finite term. So this Riemann sum becomes our function. That's how they relate. The integral is simply the limit of the Riemann sum, or the Riemann sum itself. The integral is a limit of that. So if you ever forget this part, you can always go back to the basics and do this. And it's a little bit more time consuming, but you get the answer that the same way. Is what if all of the intervals were the same size? That would be the optimal of everything we have. So we have our integral is equal to the Riemann sum as n goes to infinity of k goes up to n. All right. The reason I do this is because now we're going to fill in that part. If all of the intervals are the same size, so dx is equal to how, remember, we have our interval from A to B. How would we determine all of them being the same size? What formula would we use? Yeah, you subtract the B from A, that gives you the width from here to here, and we divide by how many we want. So if we want 10, they'll all be the same size of 10. If we want 1,000,000, we want the same size of 1,000,000. So delta x will simply be, in this equation, the limit of n as n goes to infinity so that's where our delta x equals, because it's going to be a constant. It's going to be the same value over and over and over and over. Now, this inside here has to change because it says it's going to go from 1 to n. These are my inputs. At first, my input is a, whatever that value a is. So I start off with a. Then I do the input. The next one, how do I get to the next one? Well, then I add the b minus a over n. The size, because if the b minus a over n was, say, 3, and our interval was from 1 to 5, let's make it 1. This is A and this is B. So our first input is 1. What's our second input? We start off at 1, and our step sizes are all 1. So the first one, so we have 1 plus 1 is 2. The next one is start off from here, add 1, we get 3. And the next one, we start off with this one, we add the step size, we get 4. So you see what's happening? We always start off with the first one and add the next step size. So the b minus a over n is your step size. That's what we're doing there. But we have to keep on moving. That's where we have to put a k in front of it. Because whether it's the first, third, or fifth step, that's what that's going to tell us which one it is. So this is our formula we have so far. And what does that all this stuff equal? This equals our integral. This equals our integral from a to b. That's if you have all of them the same step size. So if you have functions that all have the same width, we use this formula here to find the integral. Again, remember how we did in chapter 2 to figure out the derivatives? The slopes, we have to go through all that limits and then epsilon delta stuff, all that hard proofs and stuff. And then I showed you the shortcuts. It's going to be the same way. This is that long drawn out part that makes it hard to do. And this is a shortcut. And when I show you the shortcut, you'll think, oh, that's much easier. But first I have to show you what all is going on. The next section, integrable and non-integrable functions. What do you think would make something non-integrable? Remember, you think of this. Integration is the opposite of derivation, of derivatives. So the first derivative, we give a function, take the first derivative. We get this value here. If we take the integral of that one, we go back to the original statement. So they all they have to be similar to each other. They have to be related to each other. So if it's integrable, it's a continuous function. Why is that necessary? Why does continuity have to be a definite sticking point? What do we need to find the derivative? How do we find the derivative? What are the conditions to find the derivative? It's got to be constant. For the limit to exist, because that's the derivative, the limit. That means the limit has to be a value. It has to be able to be approached from both directions. And they have to be the same value. If it's not continuous, do they approach the same value? No. So if it's non-integrable, then chances are very good it's non-continuous. So let's look at our first theorem. Theorem 1. Integrability of continuous functions. If f is continuous on a closed interval AB, or if f has at most finitely many jump discontinuities, Then the definite integral exists and f is integrable over the closed interval. If f is continuous, that's easy. If it's continuous, then we have nothing to worry about. But here's caveat. If f has finitely many, what does that mean? Finitely many jump discontinuities. It's countable. Finite means you count them. It's not like Swiss cheese. There's holes everywhere. But now, because of this, we can take our subintervals of these. So if it's not continuous on this whole domain, then we can find a subdomain in which it is. All right, so let's look at our first example. Where's our first example? Yeah, this one is just pretty much a definition one. So we have a function f of x equals 1 if x is rational, and 0 if x is irrational. So do we have an interval which we're looking at? The closed interval. It has a Riemann sum, has no Riemann integral over the interval now. What's happening here is we see that the function is 1 if it's rational, 0 if it's irrational. What we look at here, because the Riemann integrals are Riemann sums, we have two types. We have upper sums and we have lower sums. Remember, the Riemann sums, what does a Riemann sum look like? It's the integral of the summation of the k equals 1 to n, f of ck delta xk. They're going to be the same equations, except what we put in there are the opposite ones. So for the upper sum, this is this one. If x is rational, then it equals 1. So for the upper sum, we're saying that our inputs are rational. And then for our lower sum, we're saying our inputs are irrational. Does it matter how wide the intervals are? Because our equation here is binary. It has a finite number of the condition of theorem 1. It's either a continuous function or it has a finite number of jump discontinuities. Which one does this one fall into? this function. Is it continuous? No, because we have it's either 1 or 0. It's binary. So therefore, it has to have in our interval, it has a finite number of jump discontinuities, and which it does because there are finite rational and irrational numbers inside 0 to 1. So for the upper sum, we're doing rational. What is our function equal if our input is rational? If C sub k is rational, therefore our function is equal to 1. That's what it says there. This is our f of c, and this is our x. So if we put a rational number inside there, that becomes 1. So our upper sum becomes f becomes 1. And the lower sum becomes what? The lower sum becomes 0 if we put in an irrational. So it becomes 0. So this is bottom was pretty straightforward. 0 times anything is what? 0 added a million times is still 0. No matter what we add here, delta x sub k will always give us 1. Think about it. Remember, from our intervals from 0 to 1, right? This is A and B. So our equation for delta x is b minus a over n. So far, so good. So our delta x is 1 over n. How many n's do we have? N number. So what is n times 1 over n? 1. So this becomes 1. If we have 2 of them, we have 1/2 times 2. If we have 5 of them, 1/5 times 5. It always becomes 1. So this one always sums up to equal 1. So that's how we use the Riemann sums to find the limits, the upper and lower bounds. Anything else for this function would have to be between 0 and 1. Where's the next example? Oh, theorem 2. Let's first do theorem 2. When f and g are integrable over the closed interval AB, the definite integral follows the following rules. This theorem is called the properties rule, the properties of definite integrals. And you see, these are pretty much the same as derivatives. So the properties. The first property is the order of integration. If you have a function integral that's integrated from a to b, always read from the lower to the upper. If you reverse the bounds of integration, if normally it goes from a to b, but if I reverse it from b to a, I have to change the sign to negative. The order of integration, if you change the order of integration, you change the sign of the operation itself. And it'll become more evident once we start doing these calculations. Zero width interval. Okay, remember, delta x is the width. Delta x is defined as being b minus a over n if you want to, if it's all the same size. But it's typically it's b over b minus n, b minus a. How can delta x equal 0 if what happens? So if b minus a equals 0, that means b equals a. What the zero width interval is, if I take the integral of a to a of the same function, the width is 0. Since the width is 0, the whole equation multiplied to 0. The constant multiple. Again, this is the same as what we had in the derivatives. If in your equation you have an integral of something and you can factor out a constant term, let's say all of them are divided by 3, you can factor out that 3. You can factor out that constant term and multiply by the integral, because constant terms really add no value to the final answer. It's just a multiple. The sum and difference of integrals. F of x plus or minus g of x dx. It doesn't matter what's happening there. You can, if it's easier, you can split them up and do them individually. Eventually, that's what you actually do when you have large polynomials. Instead of treating it as one big equation, you'll treat it as much as smaller equations and look at each one separately. The additive property. If my integral of this function, it gives me a weird answer, I can split it up. I go from a to c, and then I can add it from c to b, where c is between a and b somewhere. This is most often used whenever let's say we had the sine function. From negative pi to pi. If we went from negative pi to pi, our answer would be 0. So what we could do is we could take it from negative pi to 0, and then from 0 to pi. Do them both separately, come up with the answers, and then look at what's happening. So this is typically, whenever you get an integral, that equals 0. If you have an integral that equals 0, look at the graph. What that usually means is there are equal parts of it above and below the x-axis. So far, so good? Number 6. The min-max inequality. The lower bound is the lower value of the min function, of the function itself. We call it min f. It gives us the lowest value. The upper is called the max value of that function. We also always have to have the dx, which is min of f b minus a, the max of f b minus a. So obviously, we know that the min of f has to be less than or equal to the max of that function. So what goes in the middle? The integral itself. Because think about it. The integral itself goes from the minimum to the maximum endpoints. So obviously, it's got to be bigger than the lower by itself, and it's got to be less than the upper one by itself. Why is that? Because we'll see the formula for this is going to be the difference of the two. This has a lot to do with it. So the integral is between the min and max. If you want to know what the upper and lower possibilities are, that's what we're going to have. Okay, we have two functions, f of x and g of x. First, if f of x is bigger than g of x, then the integral of f of x dx is going to be larger than the integral of g of x. Just because you take the integral doesn't mean anything. It's just if the function itself is larger, the values, equal values, then obviously the area is going to be greater than the f than the g. That's the first one. That's A. B, if you have a positive function on that closed interval, then the integral of that function will also have to be positive. Why is that important? Because If you come up with a value that's less than 0, then you know that your function is less than 0. It means it's a negative. Where is a negative function? Below the x-axis. Because remember, it's the sum. If it's negative, the area is below the x-axis. If it's positive, that means it's above the x-axis, which goes into what we had earlier. If they're equal size, opposite signs, and they equal 0, or if you add them together equals 0, that means there's a good chance that equal number of it's below and above. Once you find that, we can split that. That could be our C. This is A and that's B. So these are all comes together to help us see all this stuff. The next things you see on your sheet are how that graph would look, graphically what they look like. If your integral equals 0, that means it's just the line itself. There's no area between anything. Here's your function, and you multiply it by some constant, it increases it. It changes the y. It's a vertical shift. If you add the two functions, so I'm taking this area, adding it, I'm taking a here, adding it to b, and this gives me a plus b. And remember I said earlier, if you split up the equation from a to b, you go to a to c, then c to b. This is what's happening. If you go from a to b, a to c, then c to b, this is what's happening. You're taking two separate integrals and adding them together. So this part goes from a, this goes a to c, and this goes from a to b. That's how we looked at it. The min and max, if the upper bound is this and the lower bound is this, the function has to happen between them. So, and then the domination, if f of x is greater than g of x, then the integral. What does that mean? That means the area under that curve has to be greater than that of g of x. If the function is higher than that, that means the area under these is going to be greater. All right, let's look at example 2. To illustrate some of the rules, we suppose that negative 1 to 1 of f of x dx equals 5. From 1 to 4, f of x dx is equal to negative 2. And from negative 1 to 1, of h of x equals 7. These are our givens. So A, from 4 to 1, f of x dx, what's that going to equal? What's going to equal what? It'll equal 2. Because we know from 1 to 4 is negative 2. So if we switch the bounds of integration, we got to put a negative in front of it. This we know is negative 2. So equals 2. From negative 1 to 1, we have 2f of x plus 3h of x dx. What's that going to equal? So which rules are we going to use here? here's a sum. So we could first split them up. Then the next property we use is what? It's got a constant multiple in front of it. Same as that one. Now we can evaluate them. The integral from -1 to 1 of f is equal to 5. And integral from -1 to 1 of h is equal to 7. Equals 31. Because these are given to you up here from -1 to 1. And C from -1 to 4 of f of x dx. So how do you think we're going to do this one? Do we have any integral from -1 to 4? That's f of, no, we don't have anything from -1 to 4. Can we make it into that? The sum rules, we go from -1 to 1 of f of x, and we can add that to 1 to 4 of f of x dx. We go from -1 to 1 f of x and 1 to 4 f of x. So -1 to 1 is 5. 1 to 4 is -2. The answer is 3. So yeah, you could manipulate and massage all you need, but you have to use those 3 to begin with. Let's look at example 3. Show that the value from 0 to 1 of 1 plus cosine x dx is less than or equal to radical 2. So how would you do that? What rule are we going to use? We're going to use that rule, the min and max. So what's the min of the, what is b minus a to begin with? Where do we find b and a? The bounds. Remember, it's always from a to b. So b is 1, a is 0. So this is equal to 1. This is equal to 1. So all we have to do now is look at what is the lower bound of that function. How do we find that? How do you think we'd find it? We also have to do the same thing here. Times 1. This is times 1. So let's see. Let's look at if we plug in this equation, if we plug in the lower bound. So if we get 1 plus cosine of 0, that equals what? What's cosine of 0? 1. Then let's look at 1 plus cosine of 1. How would you find the cosine of 1? Can anything be greater than cosine of 0? Think of the unit circle. Cosine of 0 is there. There can't be anything greater because 1 is the farthest it can go. Everything else after that has to be less than. So this one is going to be greater than this one. So this is going to be our min. This is going to be our max. We use radians for that. So we just proved it right there. The integral is less than or equal to is less than the max. The max is that. So there's our proof. Okay, let's look at example 4. Area under a curve. Of a non-negative function. Example 4. From 0 to b of x dx. Find the area under the curve y equals x over the interval 0 to b, where b is greater than 0. What's the only formula we know for integrals so far? We only know the Riemann sum. That's, and then I think it's next section, next chapter, next section or two. I'll show you the shortcuts to this. It's a lot easier. All right. So that's what we know so far. That's our Riemann sum formula. What do we know about this? What do we know about that? Do we know our function? What's our function? Well, we also have to define our partition. What's our partition going to be? Remember, our interval is from 0 to b. How many of those intervals are we going to have? Well, we're going to have n of them. So it's b minus 0 over n. So each partition is going to be and then our midpoint is going to be the partition times how many we have. Because the C sub k changes from each interval, it changes. So I take the partition and from here, I go to here. From here, I go to here. That's what my k represents. So let's see what we have here. We have the summation of our function going from 1 to n. Our function at C is that. And our delta x is what? This is our delta x. B over n. So that's k times b squared over n squared. Inside here, what's the only number we have to keep there? What's the only thing that changes? K, because it goes from k to 1, from 1 to n. So the b squared over n squared, I can take out in front. Does this look familiar? Did we do that in earlier? Yeah, so that was n n plus 1 over 2. This is from 5.1, I believe, when we did the summations. All right. So let's simplify all this. This becomes b squared over n squared plus n. We'll make this over 2. Now distribute. You have b squared over n squared times n squared over 2 plus b squared over n squared n over 2. The n squares cancel there. 1 n cancels there. What happens when n goes to infinity? This one goes to where? 0. So we're left with b squared over 2. So this is our integral. Our integral from 0 to b of x dx is equal to b squared over 2. Whoa. Actually, I could have showed you a shortcut to that. What does that look like if we did a graph? Because it's close. One part of it's correct. Here's our function, right? Y equals x. It goes from 0 to b. So we're looking for this area here. Remember, we limited from 0 to b, so that's what we want of this function. You're close, as you said. You had this side. You just because we limited our domain to be 0 to b, the positive side. So we can figure out the area that way. Let's see, what's the next example? Oh, this is also pretty important. The average value, we'll call that the AV, of a continuous function. So the average is this. What is it used for? Why would you use the average value of these things? What does this find? The area under the curve in this inside the intervals a to b. What we want to know is what's the average value of all those partitions. That's what this is all about. But again, not unless we have a constant function with a constant width, it's always going to change. the f of x is higher or lower, the widths could be different as well. So again, that way we would represent this. It says AV. So it's the AV of our function f is equal to this equation. This is how you'd see it. Let's look at an example. Example 5. Find the AV of our function square root of 4 minus x squared from -2 to 2. So clearly what this is asking for is looking for this. So we first find this integral and divide it by whatever b minus a is. What is b minus a? What's it going to be? It's going to be 4. So it's going to be 1 divided by 4 up in front. So now, so we take whatever we find here divided by 4, and that's going to be our answer. So the question is, what is -2 to 2 So what do we know about this function here? We've used it before, actually, earlier in this course. If we were to graph this, what would it look like? It's from -2 to 2. Let's plot some points. When x is -2, what's it going to give us? Yeah, -2 squared is 4. 4 minus 4 is 0, so it's 0. When x is 0, 4 minus 0 is 4. Square root of 4 is 2. And when x is +2, 4 minus 4 is 0. It's a semicircle. So with this one, since we know it's a semicircle, and we don't know how to do this yet, algebra, mathematics, calculus, let's solve this using geometry or trigonometry. What's the area of a complete circle? What is it? I know you're thinking it's either pi r squared or 2 pi. Which one is it? Are you sure? Anybody agree with that? What's 2 pi r then? Okay, so we pi is this. So we have 2 pi. Now, is that the circumference or is that the area? The circumference. So we could look at the area is of this function. No, forget that. So it's pi r squared. It is. The other one, 2 pi r is circumference. Yes, you're right. I said, it was when you gave it to me, answer, you were asking me the question. So it's 2 pi r. But that's this whole area. What do we need? We need half of it. Which becomes pi r squared over 2. Well, what's our radius? We know our radius is 2. So the area, which is this part of the equation, the area is 2 pi. So the average value of our function is b minus a, that's 4. And the integral of our function is 2 pi. That's the area. So what's our final answer? What's the average value? So what you're going to see also, what we're doing here is when we do integrals like this, we'll get to a point where we won't use any real math. We'll just use a table, the cheat sheet I gave you. And instead of doing the actual work, you just compare it to the table and see which one it equals. Because we're going to be looking at inverse functions, inverse trig functions, hyperbolic functions, hyperbolic inverse trig functions. So instead of memorizing all those, that's why I gave you that cheat sheet. In graduate school, we used to have a textbook about this thick that was nothing but derivatives and integrals. So that once we had to go through and look for them, and then once we found it, it's much faster than doing it by hand. Well, yeah, because you know pretty much where you're looking at. You're looking at a rational, for example, we'll get to in calculus 2, the integral of 1 over 4 minus x squared of 2 minus x. So something like this would be the inverse tangent. Again, it's much easier to use the table than trying to do it by hand, because we have a rational, we have a rational, we have a radical, and we have an equation. So it just takes a lot of time. All right, so that's end of that section. We have time. Let's look at the next one.